Welcome to the presentation on the use of internal model principle in designing pole placement controllers. We will show that the perturbation of initial conditions is handled well, but that the perturbation of gain is not handled well. Use of internal model principle to design control law is advocated. We will present Scilab code, results and some examples. We studied the magnetically suspended ball with initial conditions perturbed. We calculated the controller. We perturbed the initial conditions alone. The state x1 is the distance between the ball and the armature. The initial condition in this state is perturbed in the range of plus minus 0.005 meters, whereas x2, the initial velocity, is not perturbed. x3 is the current through circuit. We perturb that also in the range plus minus 1 amp. We found the controller to be robust to initial conditions. Then we moved on to perturb the gain. Recall the state space representation. Xn plus 1 equals Axn plus Bun, Yn equals Cxn. I have taken D to be 0 here. The transfer function is C into Zi minus A inverse into B. This is the plant transfer function. This is the plant input in Z transform, plant output in Z transform. Recall that only position is measured in our system. So as a result, the C matrix is 1 0 0. Let us design the controller for the nominal case. What is meant by nominal case? Whatever the model we assumed, namely C equals 1 0 0, and then we follow the procedure explained earlier. Using that procedure, design the controller. In that, take C to be 1 0 0. The question is, can this controller handle if C changes to 1.100, that is, this is increased by 10% or decreased by 10% to get this second case. Remember, we have to make this change at the time of simulation. That is, the controller is designed, but it is not changed. Only the gain is changed. The plant model is changed at the time of simulation. And as usual, we will experiment with a step response. So let us explain the perturbation here. We designed the controller with a nominal plant. That means these are fixed. After that, you fix the controller. Perturb the numerator of the plant, change this by 10%. Check if the previously calculated controller works. Okay, here are the experimental results. When it is increased by 1.1, the value is indicated by solid line. Remember, the set point change is unit step, so it is supposed to come here, but it has come to a lower value. Similarly, when we decrease the gain to 0.9, the value actually increases. So none of them reaches the required value, or both of them have steady state offset. So now we will explain why perturbations to gain are not handled. Recall our controller, 2-DOF controller, and also recall how gamma is calculated. Gamma is the value chosen so that at steady state the gain is 1. It is obtained as follows. But remember, our model is represented by this transfer function. We have the numerator factored as bad and good, and we have perturbed this 10%. So when we perturb this and BG fixed so that we use the same controller, this BB is changed by 10%. BB is changed by 10%. This should have been changed by also 10%. Gamma should have been changed, but we said no, we will not change gamma. We fixed the controller. The controller was fixed at the old value, but this gamma has changed. As a result, we expect this procedure not work well. Actual BB is different from the assumed BB by a factor of 1.1 or 0.9, so we expect differences. The solution to this is presented through the internal model principle, which we have already seen. In fact, I have reproduced this exact slide from one of the earlier videos. Remember, the internal model principle says that if the external signal Rn or Vn have any unstable part, that part should be present in the form of alpha in the denominator of the controller. This is the internal model principle. So here we have the step disturbance, because we are talking about tracking set point changes. Now the step input has delta in the denominator, which is 1 over Z inverse. So let us invoke the internal model principle, namely choose alpha equals delta in RC. Recall the Aryabhata's identity. Now what will happen is, because of that extra delta, we will have an extra delta in this term, first term. So RC includes delta. In other words, RC is BG delta R1. After doing cancellation and so on, when we arrive at the new Aryabhata's identity, we will have this equation to solve. In the place of R1, we will have delta R1. All other terms remain the same. Now, if you notice, delta is a known quantity because it is 1 minus Z inverse, whereas R1 is unknown. So AB into delta becomes a known quantity. Here BB into Z power minus K is a known quantity. Phi CL is a known quantity. R1, S1 are unknowns. We solve this identity for R1 and S1. The new controller is given by the following. In the place of RC, we have to put BG delta R1. Similarly here, SC by RC, we have BG delta R1. So let us calculate using this new formulation. Here are the A values for the magnetically suspended ball problem. This is the overshoot condition. This is the rise time modified, the faster one. This is the closed loop characteristic polynomial. The new Aryabhata's identity is solved now, where we have delta coming along with R1, and this whole thing is taken as the known quantity. And so the unknown is R1. We solve for R1 and S1 using our Scilab code, and we get the following expressions for R1 and S1. Then we use ball underscore im dot SCE. It uses the new function pp underscore im. After execution of that file, we design the controller. Then we invoke this xcos file. And when we simulate, we get these results. And you can see that in all three cases, that is nominal and then perturbed, increased by 10% and decreased by 10%. In all of them, the output reaches the same steady state and there is no offset at all. Of course, the corresponding inputs are not identical, they are different. With this, we have come to the end of this presentation. I hope that you will reproduce the Scilab results and that you will also work out all the steps in the derivation. Thanks for joining. Goodbye.